Okay, so in this lecture, we are going to introduce the concept of Sylow theorems. And in the first few lectures, we are going to discuss the applications of Sylow theorems, precisely applications in group analysis. Okay, that is analyzing the structure of a group depending on the order of the group using Sylow theorems. First two to three lectures will be on these applications, and then we are going to prove the Sylow theorems in details. Okay, so let us start the topic. We start with the definition. So the definition is just to understand the subgroups or the groups which are required to explain the Sylow theorems. Okay, so definition. Let G be a group. Let G be a group, and let P be a prime. Let P be a prime. Then number one is that a group of order p to the power alpha is necessarily a natural number, is called a p group. Is called a p group. We can also think of natural numbers including zero. Okay. Subgroups of a p group. Subgroups of a p group are called um, p subgroups. Are called p subgroups. Clear? Number two. Uh, Let me say, let G, the order of G, be p to the power alpha times m, such that p does not divide m. Okay. Then a subgroup of p, sorry, a subgroup of G of order p to the power alpha is called a Sylow p subgroup. Is called a Sylow p subgroup of G. Okay. And let us fix some notations. So we denote collection of all Sylow p subgroups as, so we write it as SYL p of G. Okay, and the number of elements or the number of Sylow p subgroups precisely in G is denoted as NPG. Okay, just some notations we fix. Now let us introduce the Sylow theorems. So theorem due to Sylow. Okay, so what does this theorem say? Let G be a group of order p to the power alpha m such that p is a prime and p does not divide m. Okay. Then number one, there exists at least one Sylow p subgroup. So Sylow pg is non-empty. There exists at least one Sylow p subgroup. Number two is that if P is a Sylow p subgroup of G and Q is any p subgroup of G, then there exists G in capital G such that Q is contained in the conjugate of. Specifically, if we have two Sylow p subgroups of G, then they are conjugates to each other. Then P and Q are conjugates. P and Q are conjugates. Okay. I hope you know the meaning of conjugates. There exists an element G in capital G such that G capital P G inverse is equals to Q. Number 3 is that the number of Sylow P subgroups is of the form 1 plus Kp. K is a natural number including 0. So let me just write K is greater than or equal to 0. The other way of writing this is that is the number of Sylow P subgroups. This is congruent to 1 modulo P. Right? This is congruent to 1 modulo P. And the number of Sylow P subgroups, this equals the index of the normalizer of P in G. Then by Lagrange's theorem, we can say that the number of Sylow P subgroups divides M. Right? Divides M. But this P is a Sylow P subgroup. This P is a Sylow P subgroup. There are a lot of P's, but precisely if when I denote the group, so I write it as capital P, and when I denote the prime, I denote it as small p. Okay. So in this case, this is the prime P, that is the number of Sylow P subgroups, and capital P represents a single Sylow P subgroup. Right? The importance amongst these theorems are, firstly, this one is important. From here, this statement is important, that two Sylow P subgroups are conjugates, and then this statement, that is the number of Sylow P subgroups is congruent to 1 modulo P, and that the number of Sylow P subgroups divides M, where M comes from here. Okay. We're not gonna get into the proof of these statements. We'll surely do that after 2 to 3 lectures, after we have completed the concepts of group analysis. But there are some immediate corollaries to this. Okay, let's discuss that. Corollaries. Okay. Corollaries. Let capital P be a Sylow P subgroup of G, then the following are equivalent. Number 1, P is the unique Sylow P, is the unique Sylow P subgroup of G. Other way of saying is that the number of Sylow P subgroups in G is 1, and that single Sylow P subgroup is capital P. Number 2, P is normal in G. Number 3 is that P is a characteristic in G. And number 4 is that if I consider a subset of G such that order of every element in capital X is a power of P, is a power of P, small p obviously, for all X in capital X, then the subgroup generated by capital X is a P group, right? Clear? The difference between a Sylow P group and a P group is precisely that if G has order P to the power alpha M, where P does not divide M, then the subgroup of G which has order exactly equal to P to the power alpha, this is a Sylow P group. But a P group will be any group of order P to the power some K, where K is not equal to alpha. I hope now it's clear. Okay. Clear? Where we had discussed the definition. I guess here I have written a wrong definition. I'm very sorry. That this actually arised all the confusions. Subgroups of a P group are not called P subgroups. Subgroups which are P groups are called P subgroups. Subgroups which are P groups are called P subgroups. Okay, so Now I guess the concept is clear. Okay. Sometimes I just do mistakes. I'm a human being after all. Whatever. Yeah. So we have four equivalence statements. Let us quickly prove them. I I'll refer to the lecture on automorphisms before viewing this lecture, and if possible, the concepts of group actions as well. Okay. This is a sort of mandatory because there are a few terms related to the concepts of automorphisms which we require here. For example, the concept of characteristic. Okay, and this is not that relevant for this lecture. Whatever. What is a characteristic in when the subgroup is called a characteristic in G? So a subgroup P in G is said to be a characteristic in G, and we denote this as P char G. If for all automorphisms on G, P gets fixed. Okay, P is an arbitrary subgroup of G. So it's said to be characteristic in G if every automorphism on G fixes P, right? Uh, we had certain observations related to this concept of characteristic. Let me just quickly speak of them because we will require them proof. So observations to characteristic subgroups. Observations to characteristic subgroups. Okay. Number one, characteristic subgroups are normal. Characteristic subgroups are normal. Okay. How do we deal with this? See, if you recall, there is a automorphism defined on a group, which is said to be an inner automorphism, which sends every element in G to its conjugate. Uh, Conventionally, let me denote this as X, which sends X to its conjugates, where G is an arbitrary element from capital G via sigma. So if you consider this automorphism and you consider a characteristic subgroup of G, where H is a characteristic subgroup, so it gets fixed under every automorphism. So sigma will also fix H. So this will also get fixed under sigma, but then sigma H by definition is just GH, G inverse. Right. Clear? The next observation is that if if H is a unique subgroup, of G of a given order, then H is a characteristic in G. Okay. This is also sort of a consequence of automorphisms because there is an important observation in automorphism which says that if K is a subgroup of G, then um, so suppose if K is a subgroup of G and G is an arbitrary element of G, then K is isomorphic to G K G inverse. Okay. So these observations are dealt with in the lecture on automorphisms. We just required the concept of inner automorphisms here, and the fact that the order of elements of the form order of elements of K and G K G inverse for any element G in capital G are same. Okay. So if this is what we have, and H is a unique subgroup of G of a given order, then K, the order of K and this must be same, right? So if I specifically consider the inner automorphisms, or specifically if I talk about every automorphism on G, so suppose sigma is an automorphism in G, right? Then what can we say about sigma K, where K is a unique normal subgroup of G? Then sigma of K is some subgroup of G which has order equal to K, but then that must exactly be equal to K, right? Therefore, K is a characteristic in G. Specifically, this was a specific example of this fact that automorphism sends subgroups to subgroups of same order. Okay, clear? And one more observation we have is that if H is a characteristic in K and K is normal in G, then H is normal in G. This indeed also gives a specific example when normal subgroups show the transitive property, because if H is a characteristic in G, we know every characteristic subgroup is normal, so H is specifically normal in K, K is also normal in G, but that implies H is normal in G. Now in the previous few lectures we have discussed about the fact that normality is not transitive in nature, but in case of normal subgroups we can show the fact that transitive property holds. Okay, so how do we prove this fact? Let's check. So K is normal in G, right? K is normal in G. See, observe that if I consider the inner automorphism on G, suppose sigma is an inner automorphism on G, is inner automorphism, that is sends elements to its conjugates, then sigma fixes K, right? Because K is normal. Then sigma fixes K, and sigma restricted to K is also an automorphism, on K. Need not be inner, but is an automorphism on K. But if sigma restricted to K is an automorphism on K, then that would imply that sigma restricted to K of H must equal H, because H is a characteristic in G. But then if we remove the restriction, but that implies sigma of H will be H again, if we just remove the restriction of K, right? Because sigma restricted to K is an automorphism, is a simple automorphism. We don't need the fact that it's an inner automorphism. But every element which ensures this automorphism or which ensures this automorphism are elements from G. So we can obviously remove this restriction in a way. So this holds, right? So H is a characteristic subgroup of G in a way, right? Hence it's not. So yeah. So now let us come to the proof of the corollary. So proof of the corollary. So first we are going to prove that 1 implies 2, or 1 is equivalent to 2. What was the statement 1? P is a unique Sylow P subgroup of G and P is normal in G. Yeah, that's quite trivial, because observe that if P is a unique normal subgroup, unique Sylow P subgroup is a unique Sylow P subgroup of G, then what can we say to ensure that P is normal, right? Yeah, so if P is a unique normal, is a unique Sylow P subgroup of G, then P must be a conjugate of itself, right? Because we know that if P and Q are two Sylow P subgroups, then P and Q are conjugates of itself. P and Q are conjugates. So if I talk only about P, that is if I equal Q equal to P, then P must be the conjugate of itself. But that implies P is normal in G. What we are typically doing here is that we are just putting Q equal to P here. We are just putting Q equal to P here. Nothing else. Okay. Conversely, if P is normal in G and P is obviously a Sylow P subgroup, we are not telling it's a unique Sylow P subgroup. That's what we need to prove. We're assuming P is normal in G while P is a Sylow P subgroup. And consider another Sylow p subgroup. Say Q is a Sylow p subgroup of G, but then by the second Sylow theorem, Q is a conjugate of P. But conjugates of P's are equal to P's because P is normal, so Q must equal P. So if Q equals P, Q is an arbitrary element from the Sylow p subgroup of G, then that implies the Sylow p subgroups of G contains only one element. That's exactly. So P is a unique Sylow p subgroup, right? So 1 implies 2. Now let us talk about say 2 implies 3. Okay. Sorry, 2 is equivalent to 3. That is what we actually want to show. Okay. How do we show this? Suppose if P is a characteristic in G, what was the statement of what was the third statement? P is a characteristic in G, right? Suppose P is a characteristic in G, but then we just proved that then P is normal in G. So therefore 3 implies 2 trivially, right? What can I say about the converse of this? If P is let's say if P is a Sylow p subgroup of G such that P is normal in G, then P is unique. P is unique, but then P must be a characteristic in G because we have just shown that a unique subgroup of G of a given order must be a characteristic, right? Therefore, 3 is equivalent to 2. Thus, we have shown that 1 is equivalent to 2 and 2 is equivalent to 3, right? Now we show that 1 is equivalent to 4 and then we will complete our cases. So now we want to show that 1 is equivalent to 4. Okay, how do we show this? Let us choose a subset G such that order of x is a power of p, small p, for all x in x. But then if I consider the cyclic group generated by each of these elements x, then that is a p group, right? But if it is a p group, then it must be contained in the conjugate of capital P by the second Sylow theorem. This implies x must be contained in the conjugate of capital P. But the conjugate of capital P must exactly equal P, right? Because we have assumed 1, and assuming 1 is directly assuming 2 as well, because 1 is equivalent to 2, right? So if x is inside P for every element in capital X, then that would imply the cyclic group not the cyclic group, the group generated by X is, because we do not know how many elements are there in X. So the group generated by X must be contained in P, right? What can we say about the converse? Suppose X is a, or in a way this implies that this is a P group, right? This is a P group. This holds from Lagrange's theorem, because if this group is contained in P, indeed it's a subgroup of P, right? It's a subgroup of P, because it will be a subgroup of G and P is also a subgroup of G, so by transitivity it holds. But then a subgroup of P will have ordered some power of P, right, by Lagrange's theorem. Therefore this is a P group, right? Therefore 1 implies 4. What can you say about the converse? Conversely, what we do is that we assume X to be the union of all Sylow p subgroups. So let X be the union of all Sylow p subgroups of G. Okay, then that implies clearly P is a subset of X, right? Or I should say if X is the union of all Sylow P subgroups of G, then what more can I say? Yeah, I can typically say that P is a subgroup of the subgroup generated by X. Correct. Yeah, correct. Right. I can say this. So, um, uh, so we are assuming four holes, right? We are assuming four holes. X. So if four holes, then the subgroup generated by X is a P group. So this is a P group, and we are assuming X to be the union of all Sylow P subgroups of G. Then P is contained in the subgroup generated by X. Yeah, correct. That's correct. That's correct. That's correct. Okay. Conversely, let me just specify that if four holes, right? Okay. But P is the P subgroup of G of maximal order. But P is the P subgroup of G of maximal order, because the maximal power of a prime in the order of G is P to the power alpha, and the order of P is exactly P to the power alpha. But P is the P subgroup of G of maximal order, right? And that is the order which X can comprise, because X is the union of all Sylow P subgroups. So that's the maximum order which X can comprise of. So that implies P must be exactly equal to this, right? Which implies that 4 implies 4. Right. So how do we prove this statement specifically? So we show that 1 is equivalent to 2, 2 is equivalent to 3, and then we show 1 is equivalent to 4. Right? Clear? Let us talk about a few examples. Can we talk about Sylow subgroups of S3? Observe that S3 has 3 Sylow 2 subgroups. S3 has 3 Sylow 2 subgroups, which are the subgroup generated by 1, 2, the subgroup generated by 2, 3, and the subgroup generated by 1, 3. This you can check from the fourth statement. That is, if I consider a set such that every element of set has ordered a power of some prime, then I can say this. Right. Yeah, this you can verify from 4. S3 has number of Sylow 3, so I guess it's 1. Yeah, S3 has a unique Sylow 1 subgroup. Sylow 3 subgroup. And it's precisely 1, 2, 3. Subgroup generated by the cycle 1, 2, 3. What is the order of S3? It's 6, right? So it's 2 into 3. Right? We're talking about Sylow 3 subgroups, right? We're talking about Sylow 3 subgroups. Then the number of Sylow 3 subgroups, say N3 of G, where G is S3, then it should be precisely of the form 1 plus 3k. And this must divide the other element in the order. So this must divide 2. But observe that this is only possible if k is equals to 0. And that would imply that N3G is equals to 1. Right? The only possibility is this. And hence this observation is obvious. Right? Okay. You can also verify this statement out from this concept as well. That is, if I consider the Sylow 2 subgroups, then this must be of the form 1 plus 2k, but this must divide 3. So the possibilities of k is either 0 or 1. But if k is 0, then you must have a unique Sylow subgroup, unique Sylow 2 subgroup. And if k is 1, then you have 3 Sylow 2 subgroups. Specifically studying the group structure, we find that there are exactly 3 Sylow 3 subgroups, Sylow 2 subgroups. Clear? Okay. Moreover, there is one more important observation in this case, which is that if I consider S4, then the number of Sylow 2 subgroups, suppose I consider G to be S4, the number of Sylow 2 subgroups of G is 3 and number of Sylow 3 subgroups of G is 4, right? Also, every Sylow 2 subgroup of S4 is isomorphic to D8. Try and verify this out. Okay, because observe that what is the order of S4? It's 4 factorial, right? It's 24, right? So it's 2 cubed times 3. So the Sylow 2 subgroup will have order 8, right? So the order concept is clear, right? So the order concept is clear, and hence try and find out an isomorphism from the Sylow 2 subgroup of S4 to D8. Clear? Okay. Let us come straight to the applications of Sylow theorems. So applications. So we want to talk about the group analysis. The group analysis. Number one, every group of order PQ where P and Q are prime, where P and Q are primes, such that P is less than Q and P is less than Q. One second. So P is less than Q and P does not divide Q minus 1. Then is cyclic. Then the group is cyclic. So every group, say G of order PQ, such that these conditions hold, then is cyclic. That is, then G is isomorphic to ZPQ. Okay, we are going to verify this. Okay, so let the order of G be PQ such that P is less than Q. We will impose this condition later. Okay, such that P is less than Q. Both are primes. Both are primes. Clear? Now, let P be a Sylow P subgroup of G, and let Q be a Sylow Q subgroup of G. Okay. What do we try to show is that if Q is normal in G and if P is normal in G, then G is cyclic. Okay. Let's see what observations we have about this Sylow Q subgroup. What should be the number of Sylow Q subgroups? See, NQ is 1 plus KQ, right? NQ must divide P from the second Sylow theorem, from the third Sylow theorem. And one more thing we have is that P is less than Q. These three are things which we already have, right? Okay. So if 1 plus KQ needs to divide P, 1 and 2, or rather these three in fact, because P is less than Q, right? 1, 2 and 3 implies that the only possibility for K is 0, which implies the Q is a unique Sylow Q subgroup, which implies Q is normal in G. Because for 1 plus KQ to divide P where P is less than Q, the only possibility for K is 0. Correct? What can we say about NP? See, NP must divide Q, right? NP will have the form 1 plus say LP, So what are the possibilities for L, right? See, NP can surely be 1, LP can surely be 1, and we are dividing Q, right? We need a factor of Q, but then NP can either be 1 or Q, correct? Then NP can either be 1 or Q, right? But for NP to be equal to Q, that would imply P divides Q minus 1. If NP equals Q, then that would imply P divides Q minus 1, because NP is congruent to 1 plus, sorry, NP is equal to 1 plus LP, but for this to divide Q, we must have P divides Q minus 1, right? Therefore, we impose the condition we have, but let P does not divide Q minus 1. Then the only possibility for NP is 1, or in other words, P is normal in G, right? So we have P normal in G and we have Q normal in G, right? Now both are of prime order, hence cyclic. We know that elements, groups of prime orders are cyclic. So let capital P be generated by some element small x and capital Q be generated by some element small y. Now there's a very important observation under automorphisms. Observation. The observation says that if H is a normal subgroup of G, then G modulo the centralizer of H in G is isomorphic to automorphisms of H, or rather I should say subgroups of the automorphisms of H. Okay, subgroups of the automorphisms of H. Yeah, let me just write it in that way. A subgroup of automorphisms of H. Now since P is normal in G and P is a cyclic group generated by X of order small p, what do we have? Therefore we have that G mod the centralizer of P in G is isomorphic to a subgroup of the automorphisms on ZP, right? Because P then will be isomorphic to ZP because P is a cyclic group of order P, right? But a subgroup of the automorphisms of ZP will have order P minus 1. The latter has order P minus 1. Then by Lagrange's theorem, what can we say? Then by Lagrange's, see, I do not want to say this. I actually want to say something more. See, if these two are isomorphic, right? Then, but observe, P doesn't divide P minus 1. That's trivial, and Q also does not divide P minus 1. This is something we checked, right? From the observations, right? Therefore, the order of G mod the centralizer of G must be 1. So any non-identity, what I mean to actually say is that any non-identity subgroup will have order P minus 1. But P doesn't divide P minus 1, Q doesn't divide P minus 1. So the only subgroup which it should be isomorphic to is the trivial subgroup. Hence the order must be 1, or order of G must be equal to the order of, so this is P, order of the centralizer of P in G. But since the centralizer of P in G is by definition a subgroup of G, so G must equal the centralizer of P in G. But if G equals the centralizer of P in G, what does this immediately mean? This immediately means that P is inside the center of G. This implies P is inside the center of G, but P is generated by X. So X is in the center of G. But if X is in the center of G, then this implies X commutes with Y. But if X commutes with Y, then this implies order of XY must be order of X times order of Y. Order of X was P, order of Y was Q, so it's indeed PQ. But that means, but XY is an element from G, right? So there exists an element in G of order PQ, and order of G is itself PQ, so that means G is a subgroup generated by XY, and the order of G is PQ, but this means G is isomorphic to ZPQ, right? Clear? Now let us talk about the next group which we want to discuss now. Okay. So number 2, a group of order 30 has a normal subgroup of order 15. Groups of order 30 has a normal subgroup of order 15. Let's verify. Okay. Okay. Let me use a different color. Will this do? Yeah. This is much dark. Use a fine color. Let me use. Okay, let me do it with pink. Will it do? Yeah, seems fine. Okay. So let me use. Yeah, let me verify this out. Okay. First things first, observe that. So we need to show that a group of order 30 has a normal subgroup of order 50. So let G be a group of order 30. Let H be a subgroup of order G such that the order of H is 50. But then observe, then the index of H in G, which is given by the order of G by order of H, this is 2. But recall we had shown that subgroups with index 2 are normal. But this implies then H is normal in G. So to show that there exists a normal subgroup of order 15, it suffices to show there is just a subgroup of order 15. Because if there exists a subgroup of order 15, then it's indeed normal. Therefore, it suffices to show there exists a subgroup of order 15. Now I'm not liking this color much. Let's use this blue. Okay. Clear? Now see, the order of G is 30, so it's 2 times 3 times 5. Right? Let P be a Sylow 5 subgroup and Q be a Sylow 3 subgroup. Okay. Clear? Now observe that if P or Q, one of them is normal in G, then PQ is a subgroup of G, and if see, PQ is a subgroup of G, and what should be the order of PQ then? It should be 15. Why is it so? Because let me just verify this out. Let me just verify this out. See, we know that. See, if suppose Q is normal in G, but that implies the normalizer of Q in G is equal to G. Therefore, now by definition P is a subgroup of G. This implies P is a subgroup of the normalizer of Q in G, but this implies P normalizes Q. P normalizes Q. Recall from previous lecture we had shown that if P normalizes Q, then PQ is a subgroup of G. Moreover, what is the order of PQ? It's given by order of P times order of Q by order of P intersection Q. But observe that P is a Sylow 5 subgroup. It has order 5, right? Q is a Sylow 3 subgroup. It has order 3. So the intersection happens only at the identity element, right? The elements in P and the elements in Q specifically, uh, you know, uh, P is a group of order 5, which is a prime. It's a cyclic group trivially. Q is similarly a cyclic group of order 3, right? So you can just view at the orders, they are co-prime to each other, right? 5 and 3 are co-prime to each other, right? So generators having order co-prime to each other. So the only intersection between P and Q can happen at the identity element. So that means P intersection Q should be 1. So that must be equal to order of P times order of Q. But order of P is 5 and order of Q is 3. So it's clear this part? Okay. So now observe further that now if P and Q are P or Q are normal in G, then P and Q both are characteristics in PQ. This is an observation which directly comes from the fact that P and Q are unique subgroups of PQ, hence are characteristics in PQ. Okay, these are unique subgroups of PQ because there can only be one subgroup of order 3 and one subgroup of order 5 inside PQ. You can just verify this from the third Sylow theorem. Then P and Q are characteristics in PQ. Right now, PQ is normal in G. Right, PQ is normal in G. Why is it so? Because PQ has order 15. PQ is order 15. So if PQ has order 15, then the index of the subgroup PQ in G is 2, but then PQ is normal in G. Now recall the properties of characteristic subgroups we had spoken of, that if H is a characteristic in K and K is normal in G, then H is normal in G. So if P and Q are characteristics in PQ and PQ is normal in G, then that would imply both P and Q are normal in G. But if both P and Q are normal in G, then we have our proof, right? Basically, we have our proof right from here as well, right? Because PQ has come out to be a subgroup of order 15, which is, uh, so PQ comes out to be a subgroup of order 15, which is normal in G, right? But how does this, we derive at this, we reach this conclusion that PQ is a subgroup of order 15, which is normal in G. For this to satisfy, we need to have that either P or Q are normal in G, right? But the observations come right from here that if P or Q are normal in G, then directly we can say that both are normal in G, right? So how do we say that this is the exact possibility we need to talk about? We come to this by contradiction. We say that neither P nor Q are normal in G. Let neither P nor Q be normal in G. So if we reach a contradiction to this, then we have that either P or Q are normal in G, but then P and Q are characteristics of PQ, and PQ is the subgroup of order 15, which is normal in G. Right? Clear? So let neither P nor Q be normal in G. Okay. Now, by the third Sylow theorem, what is the probable number of Sylow 5 subgroups? Observe that it's 6 and this is 10. Right? Number of Sylow 3 subgroups is 10. Because we need to make up a total number of elements of 30. You need to get that in mind. So each of these elements have 5. So the order of number of elements in each Sylow 5 subgroup is 5. Right? Okay. Now each element each element of order 5 is in P. Therefore, number of elements of order 5 in G, this must equals the number of non-identity elements in each Sylow 5 subgroup, right, times the number of Sylow 5 subgroups. So we have 6 Sylow 5 subgroups, and the number of non-identity element in each Sylow 5 subgroup is 4. This implies we have 24 elements of order 5 in G. By the same observation, by similar observation, there exists 20 elements of order 3 in G, because the number of elements of order 3 in G will be the number of non-identity elements in a Sylow 3 subgroup times the number of Sylow 3 subgroups. So the number of non-identity elements in a Sylow 3 subgroup is 2, and there are 10 Sylow 3 subgroups. But this already gives us 44 elements in a group of order 30, which is not possible. 30, which is absurd. This implies either P or Q needs to be normal in G, and we have our justification. Okay. So let this lecture be up to this much. In the next lecture, we will be doing some more group analysis. So meet you guys in the next lecture.